we derived this big, beautiful equation in the last video, and what we're going to do now, like I mentioned, is we're going to look at little pieces of it. All right, so we're going to look at this piece right here first. All right, and our condition is that the EMF is 0, so that means this term here is wiped out. Now that's going to happen whenever you've got the a type of situation shown there at the left. All right, so we're going to have to start out with some kind of charge on our capacitor, and then whenever we close the switch, okay, so just sort of imagine we've got positives here, negatives here. Whenever we close that switch, all right, current is going to flow back around this way, okay, from positive to negative. Okay, and so of course that's our resistor R, capacitor C. All right, so let's first think about the current that's actually flowing. Now we've got an equation that deals with charge, okay, and that might seem kind of weird. Our charge is some Q naught e to the minus t over r RC. And we might be like, okay, so what do we do with this? Well, remember that our current is the time derivative of our charge. Okay, so if we take our derivative, we've got dq dt becomes our I. Okay, Q0 is just a constant. All right, then we want the derivative of our exponential function. Okay, and just to sort of refresh your memory there, if we go d dx onto e to the ax, what we end up getting is a e to the ax. All right, so what we have to do is whatever is up here gets pulled down in front when we do our derivative. So in our case, the thing we've got up there that we have to pull down is this 1 over RC and the negative sign. Okay, so we're going to pull those down. So I'm going to put minus 1 over RC. Okay, so there's our A term, minus T over RC, just like that. Okay. All right, now let's massage this just a little bit. And we can say that I've got Q over RC. So I, okay, becomes negative Q over RC, but for a capacitor, remember that Q is equal to C delta V. Okay, and so let me write this, finish this at minus T over RC. Okay, now I want to take this expression for Q and I want to plop it in right up here. So I'm going to get minus C delta V over RC, and you can see my C values are going to cancel there. All right, so I get this nice thing right here, minus delta V over R. Okay, and that's the voltage on the capacitor, by the way. Here, E minus T over RC. Okay. So if we know the initial charge on the capacitor, Q0, then we can figure out what our current is at any time. Or if we know the voltage on the capacitor when we begin, we can do that trick right there. Okay. Either way is fine. So we got lots of ways to go with that. Okay. Now what matters is, let's tie this back to how we started. All right, so if I put time here, my charge Q0, all right, it's going to go drop off just like this. Okay, that's what my equation up here tells us. So I have an exponential decay that's going on there. All right, now the current, all right, the minus sign means it's traveling around the other way, but you can see I'm going to have a decaying current there as well. So I0 is going to come down like this. Okay. Now, there's one more thing that we're going to do with this while we're doing stuff. And that is, I want to take this value for R and I want to put it over here on this side. So I get IR, and that's equal to minus delta VC, e to the minus T over RC. Now, I over R there, this right here is my voltage across my resistor. Okay, so we could say delta VR is minus delta VC e to the minus T over RC. Okay, just like that. Now, truth be told, the negative sign both here and here aren't all that important, because most of the time we're going to be interested in the magnitude of the current. Okay, we know it's going to go around backwards or whatever. Okay, or that the voltage is going to be pointing in the opposite direction. So most of the time we're interested in the magnitude of that thing, just like that. Okay. All right, so I'm going to end this one here, and we're going to do one more case, and then that'll wrap it up.